Okay, good morning. So last time we talked, we went into non-steady state systems in a little bit of detail. I just wanted to revisit that for a brief moment here because I couldn't remember exactly how they derived or defined C at time infinity. It turns out it was very simple. If we take a look at a graph where we're looking at some concentration versus time, and maybe that's milligrams per liter or something like that. And we consider what happens at steady state in a system. Of course, at steady state, you've got a flat line. Whatever concentration is in there, it's constant. Then if you perturb that with some sort of a step input or change, maybe you instantly add a bunch of this material into the system, then the deal there is, well, if nothing else changed, you just added a bunch extra for a moment, then what's going to happen, you expect it to come back to the same steady state condition. And so you'll very likely see something like this, and then it'll flatline again. And so really what we're talking about for C infinity is the C at once it reaches equilibrium again. So the C at the point where dc dt goes to zero. You need enough time for that, of course. So when they were deriving some equation for this in our book, what they were assuming was, well, let's say we have a system that is a CSDR, so you got an input and an output. It's well mixed. And then you have a growth reaction and a decay reaction. And they said, well, it's pretty common to have first order decay. That's pretty common in our systems. And zero order growth is probably the more common if we're dealing with growth equations. So they just assumed there's one of each. That's where we got this equation here. And I probably wrote it out differently last time and probably included a C here because I didn't realize the book was assuming that zero order there. So with that, it becomes pretty simple to solve for C and call C at infinity. So that's all it was. So what they did was they just took this governing equation, our accumulation rate in that system, inputs, outputs, minus a decay reaction plus a growth reaction. They said C in the reactor here is C at infinity once we reached steady state. So when dc dt equals zero, so we find dc dt equals zero out here, we no longer have any more change. So then it was just a matter of solving for C. So pretty much what we had done before. But in that case, they were also including this decay rate and a growth rate. So just wanted to touch on that because it was, I know that I left that confusing last time. From there, you can derive some other stuff and manipulate it. Maybe you find at what time, find C at a given time, stuff like that. But you'll probably, in that case, make use of the fact that you can know C at time infinity based on this stuff without doing any integrals. Okay, so just wanted to come back to that. Today, primarily, I want to target sedimentation. And I looked at our schedule on the syllabus, and we're a little behind, so I'm going to try to get into coagulation as well. I did post these slides, so if you're following along on a computer, feel free to load those up. They're on Moodle. I have not posted your homework yet, but I will today. It'll be your first homework, and we're really just going to have the one homework before the exam. Typically, the way I organize the classes, I do more review for the civil students, and they need more time catching up with chemistry and stuff. So it's going to be one homework set for the first exam, where I normally do two. And the reason I'm saying that is typically I aim for about 4, maybe 5 homework assignments for the class, and this time, given just how crazy and weird it's been, it might just be 3. But if you feel like you need more, or perhaps additional great opportunities, we can certainly talk about that. But so far, it feels like 3 might be the natural fit, or I could maybe split the second exam materials into 2, perhaps. But for now, this should be just the one homework for the first exam, and we'll go over that before we have the exam. Okay, so sedimentation today. Really, what we are concerned with when we're talking about sedimentation is using gravity. So kind of the first option that's available to us. It makes the most sense. It's pretty much free. I mean, you need the space to have the water and the pumps to, push it through at the right rate, but gravity is quite simple. If we think about what we can settle with gravity, we will work towards a force balance, but essentially you can imagine having particles of sand, of silt, small debris, whatever it is. We're going to have some particle, and the goal is to have it either settle, or in some cases we might try to float it by adding bubbles and do like an air flotation, kind of reverse sedimentation. And essentially what we're going to do for the class to make it easy on ourselves is to assume it's a sphere. Okay, there's quite a lot you could get into in terms of different classifications of sedimentation. We're not going to deal too much with that. Just briefly, I'll say there's like type 1 sedimentation is your ideal spheres. Nothing weird is happening. They're not colliding during the process. It's just them settling. And that's primarily what we're going to deal with. Then there's like type 2 where, okay, you have them settling, but maybe also they're colliding together. And then there's like 3, 4, and 5 where you have different dynamics. Maybe there's so many particles settling that they get into kind of a blanket and then catch each other. There's different things we can get into. In terms of the math, we can do math for type 1 sedimentation because we can simplify it with certain assumptions. The other types, we can't do math from first principles. We have to do like observational, empirical. Like I tested it this one day and it settled at this speed for a little while and then it slowed down. And we have some empirical relationship with, something about the particles, something about what's happening, and we derive some equation based on the observations. Here we can, with the type 1, which we're going to cover and use for this class, really we can take it from a force balance of what forces are acting on a particle, assume it's spherical, and then we have a pretty nice equation for that can account for different parameters. So we're going to assume spherical. Okay, so thinking about what forces are going to act on a particle, first of all, gravity, of course. Then we're also going to have a force of buoyancy. So we have FB here. The buoyant force is essentially going to be related to the volume of water it occupies and then the mass of the water it's displacing. So whatever mass of water that particle is displacing is going to act on it with an upward force. So it's kind of like the gravity of the water it's displacing going upwards instead. And then depending on which direction the particle is moving, and in most cases we're going to say we want them settling downwards, we're going to have, so if the motion is downwards, then we're going to have a force of drag that is directed upwards. So those are going to be the 3 forces we're interested in. And you probably remember seeing force diagrams like this from physics. And in physics, you probably did a problem at some point looking at the free fall velocity of somebody skydiving before they open their parachute. So you can imagine the same type of dynamics going to happen here. It's just you're going to have in addition to the force of drag versus the force of gravity, which, maybe a person skydiving, maybe it's like 100, 200 miles per hour that they'll reach, something like that. For a particle, you're going to have this force of buoyancy, which you're not really going to experience much of as a person in the air as a fluid. I mean, technically it's there, but it's pretty minute. So in this case, we're going to have the same dynamic, and the drag will increase as the particle accelerates, or the speed of the particle increases. But the force of buoyancy will also be pretty important. So those three forces, and essentially what we want to do is find the terminal velocity. So we'll reach a terminal velocity once the force pulling downward is equal to the sum of the forces pushing upward, right? So that's pretty basic here. We can say the force of gravity is equal to the force of the drag plus the force of the buoyant force. So then we can define each of these forces based on a particle, and that becomes easier if we assume that it's a spherical particle. So the force of gravity is going to be the mass of that particle times acceleration due to gravity, so mg. And there's actually a more convenient way than dealing just with the mass of a particle, because it's hard to measure the mass of something very small. If you've ever worked in a lab, maybe you've got a nice laboratory scale and it can go down maybe to milligrams, maybe 0.1 milligrams. If you go really, really fancy, maybe you can get like 0.01 milligrams as your detection limit, and you have to have like a very stable surface and a very stable area so there's no vibrations changing your mass detection. Well, consider weighing a speck of dust that's in the water that you're presuming may settle. You try to measure the mass on that, you're just not going to be able to. Not to mention you have to take it out of the water. So instead of doing that, what we can do is take some observations about the particle, which is actually pretty easy to do. You can watch with fancy systems and probably simpler ways than this light scattering technique that I'm thinking about. But essentially, we have ways to see how quickly particles are vibrating or moving around. We can get some information about their size, and then how quickly they're moving around will give us some information about, okay, what's that particle's mass? So we can derive the mass in some sense. Or excuse me, the volume part of that is fairly easy. We can get something about the density as well, especially if we were to collect a bunch of the particles on a filter, we can kind of get a bulk density for them. So getting that volume and that density then gives us a reasonable metric of the mass, reasonable representation. So if we get density from something like filtering a bunch out and kind of measuring the density there, and we can have some assumption about the volume, maybe we do some fancy observation for the size, or maybe we just do some filtration and see what size filter is actually removing them. Whatever the way, we can get something pretty easily about the size, we can get something pretty easily about the density, and then those two together can give us the mass. For the buoyant force, kind of same principle applies. If we do have that volume for the particle, so the buoyant force is going to be the mass of the water displaced times that acceleration due to gravity. And if we get that volume of the particle that we wanted, we then need the density of the water. So we have rho here versus the rho for the particle. That's going to give us what we need for the buoyant force. Last would be the force of drag. And here, essentially what we use as the force of drag is 3 times the dynamic viscosity of water, and I'll have all these written out in a moment. That mu times pi times the velocity, so Vs being the velocity downwards, so the settling velocity, times the diameter of the particle. Okay, so if we relate all of these, so here's all those parameters written out for you. One thing to note here is the density of water is going to be temperature dependent. So we'll have a lookup table for that. The viscosity of the water will also be temperature dependent. So I'm going to add this here as well. So we'll have a couple parameters that we need a lookup table for given the temperature of the water. Hotter water is a little bit less viscous, so particles could potentially settle a little quicker in hot water. Density of water is a little bit lighter as you heat it up. Typically, I mean, there's a little bit of a difference as you get close to zero, but that's the general trend as well. So then you have a smaller buoyant force as you get hotter. Okay, so if we relate and say, what does our equation look like when we have the force of gravity equals the force of drag plus the buoyant force, we can solve for that. I think I have space on the next slide, yeah. And essentially, we can derive an equation to get us that settling velocity. That's kind of what we're targeting, is how fast are these particles going to settle? Because if we can know that, then we know something about how to design a sedimentation basin, right? That's ultimately the thing that we're really interested in, is how fast are these particles going to settle? Then we can map, okay, how much distance are they going to have to fall? How much time do we need to give them to do that until they hit the bottom, and we can separate them kind of physically from the rest of the water. So let's do that. We have mass of the particle. So I'm going to, actually we're going to do the, we're going to start with the right side here. So we're going to go with, for the force of gravity, this would be the volume of the particle times the density of the particle times the acceleration due to gravity. It's going to be equal to v particle times rho times g plus this 3 mu times pi times that settling velocity that we're interested in times diameter of the particle. Okay, so this Vs is really what we're interested in here. So we're going to start solving for that. We'll go ahead and say 3 mu pi dp times Vs is going to be equal to volume of the particle times rho g minus volume of the particle times the density of water times gravity. We can simplify, solve for Vs here, and say Vs is going to be equal to, we'll go ahead and take the volume of the particle and the acceleration due to gravity outside, factor those out. Say this is going to be rho, the density of the water minus the density of the particle. All that divided by 3 times mu times pi times dp. Okay, so that's one form of it, but it would kind of be nice if we could, we have a volume of the particle there and we have a diameter of the particle there. And it would just kind of be nice to simplify that to just have diameter of the particle. So we can do that if we remember that we're assuming that it's spherical. And we're also making some other assumptions based on the viscosity, the turbulence, things like that. We're assuming we don't have turbulent flow. We just have slow laminar flow. Particles are not going to be disturbed by motion in the water. Otherwise, it's just that stuff. So there's a few assumptions going on here, but overall, it's just to simplify the situation. Okay, so assuming that we do have a spherical particle, the volume of a sphere is what? Pi. If we do diameter of the particle cubed, that's, what was it? Well, if it's r squared, then it's 3/4, is it? 3/4 pi r cubed? Yeah. Okay, so if we've got r there, that's what it looks like. But if we take r over 2, that would be pi over 6 diameter of the particle cubed, I believe, right? I think it works out that way. Because you take 1 over 2 cubed, that's 1, so that's 2 cubed is 8. 8 times 4 is 24. 3 divided by 24 is 1 divided by 6. So that, yeah, that should work out. Okay, so with that, we can take our volume term here and just simply insert pi dp cubed divided by 6, and that's going to tell us that we have g, and I'll fill in the other parts in a moment, times rho minus rho particle. We have dp cubed, but there's a dp on the bottom, so this is going to change to dp squared, divided by 6 times 3 is 18, mu, and the pi's cancel, and that dp we already canceled. So that's going to be our end equation. And I'll give you that equation on formula sheet. I believe I've already posted the formula sheet to Moodle. If I have not, I will do so today. But I think it should already be there, so you can kind of see what you're going to have for the first exam in place there. So that's our final solution, and this is what we'll use when doing sedimentation in this class, and with regards to finding the settling velocity if we have some information about the particle dimensions. We can use this for quite a few things, and as you see, we've got a couple temperature dependent parameters in here, the rho for the water and the dynamic viscosity. And we could maybe do this on the moon and recognize that the force of gravity is not very good on the moon, so this probably would not be a very effective treatment option if you had to treat water on the moon, for example. Okay, so what does this look like if we put it into practice? Well, there's a couple of reactor designs that are most common. Sedimentation is used often in both drinking and wastewater treatment. A lot of times in wastewater treatment plants, you'll see circular sedimentation basins, clarifiers, you could call them. And I think it just is partly just a common practice. Perhaps since they're settling a little bit more solids, maybe it's a little easier to make these conical at the bottom and then remove particles that way. It's really going to depend on what type of particles you're removing, what kind of land you have, what makes sense. But really, if you have a circular or a rectangular system, you can still look at a profile of how a particle will settle as it goes from your starting point to the ending point. So in a circular clarifier, by the way, most of the time water will be spreading out from the center point. And so any radius away, you're going to have essentially water flowing directly away from that center point to the edges and water collected over the edges, whereas in a rectangular basin, you just have water flowing straight across. And if you take a look at a cross section, so by cross section I mean, so both this one on the right is an aerial view, so you can't really, the cross section would literally be looking down into that line I drew, and how deep is it going down into there. You can kind of see it a little better with this angled view if I were to draw and say, let me get rid of this other line. If I were to say this goes some depth and it goes to the wall here and that wall goes down, we could imagine the cross section there for particles traveling that way. And the question is really, how fast is it moving to this, as the water moving, compared to how fast is the particle moving? Is the particle going to hit the ground and be separated before it reaches the end and flows over the edge of the system? So in both cases, you just have water flowing from left to right, or whatever direction, and you're going to be interested in, that highest particle that starts at the top of the water column. Is that particle going to settle fast enough to escape the reactor like this one just did, or is it going to be, actually going to be able to be settled and removed? So, sorry, I said fast enough for this one. I should have said slow enough. Is it traveling slow enough so that downward that it's going to escape, or is it fast enough that it's going to be settled? Is kind of the question. So, with that in mind, we can take a look at how we might describe this mathematically and relate our settling velocity to the parameters of a sedimentation basin. So what I'm going to do here is, and for the next few slides, is I'm taking this rectangle to be that cross section. So height is here on the y-axis. We could imagine if this was a rectangular system, we could draw the rest of the system out this way, and it would be that box-like basin, right? And we'd have some area, and water would be flowing through this way. Okay, so that's kind of the example that I'm using here. And what I want to focus on is simply the particles passing through this system. So we have the total height of the system, h here. We have HP being the height of a given particle. And a lot of times we'll say the particle that's at most risk of escaping, if we want to design a system to remove every single particle, then what we need to do is consider when the particle is at the top. So that's where we say for complete removal, HP equals H. Okay, so but we could also look at some particle down here and say that's HP, the height of that particle. That's what I mean when I say HP, and that's how we can relate it to the overall height of the reactor or the basin. Okay. The next thing to consider is how we can relate the height of the particle to the system's flow rate and how long the particle is going to have in the system and how fast it's settling. So if we want complete removal, we have to assume that we go from the very top, and the very slowest we can go downward and have complete removal is the line that connects essentially this diagonal. So it goes from here to here. That is the slowest sedimentation velocity that gives us complete removal, because if the particle up here is settling at that speed, and we're going to assume, I mentioned we assume spherical particles earlier. I should also mention we're assuming they're all the same size. So I'm going to just write that in the corner here. One of the assumptions for type 1 sedimentation is assume all particles are essentially equal. The same size. Okay. So if they're the same size, the same density, all of that, then they're going to settle at the same speed. So that means that a particle here is just going to do the same thing, same speed, and just be settled earlier, right? So it doesn't really matter anything that started below the full height. If the full height is settled, everything else is going to settle. That's kind of no problem there. Okay, so what we can do is use our hydraulic retention time to know how long water is going to stay in the system. We're assuming there's no mixing going on. It's just a slow laminar flow. We've just got water flowing from left to right. And given that flow rate, what we might consider is that our theta is going to be V over Q, We know that. So if we have a flow rate and we know something about the volume of this chamber, then we should know how long we have for the particle to settle, right? How long it's going to stay in this basin, and the velocity just needs to be fast enough so that it hits the bottom before or by the time that the water leaves the system, right? That's ultimately the design criteria. So that's how we relate a critical settling velocity, meaning that critical velocity that we have to meet. It's the minimum velocity to get complete separation, complete removal of the particles. So this critical settling velocity, that's our design criterion. We're going to say that V naught is going to be equal to, well, let's describe it this way. We'll say the downward velocity for the complete removal for that complete removal for the minimum, like the minimum speed at which you achieve complete removal, that's V naught there. So what we can say is the settling velocity for the particle is equal to V naught. This is complete removal and really it's the minimum velocity for complete removal. Let's say minimum. Okay, does that make sense? Okay. All right, so then from physics, we can just take a look and say, okay, well, we need to, for the particle to travel the distance h, and we have some time, and our time is going to be theta. So with that in mind, the distance and time, velocity is distance over time, we can relate and say then, we can say that Vs is, if we get separation or the removal, Vs, we have traveled h distance over theta time. Okay, so that's, and again, that would be our design criterion if that's exactly the case. Now, if we had a problem where perhaps Vs changed, we suddenly have a different temperature or suddenly have a different size particle, then our Vs is going to change. Then we would say, oh, well, we need to change the height, or we need to change the hydraulic retention time. We have to decrease the flow in order to still have the removal. So just keep in mind that when we talk about V naught, that is the precise design criterion, and Vs is the observation we make. And a lot of times we'll relate the two. Just try to keep that concept separate in your mind, that Vs is observed or calculated velocity, and V naught is that critical or design velocity. And again, we relate them often because we might want to design the system to remove precisely one type of particle, right? Okay. So, what happens if our V naught is greater than Vs? So if the velocity that is exactly the speed that we need is more than the particles are settling, then not everything's going to get removed, right? Because we have V naught being this one here. Assume that's straight. if that velocity is greater than the velocity term for some other particle, so if this is Vs, we'll say Vs1. We see here V naught is greater than Vs1. That means that particle escaped, right? So we know that if we compare the two, we compare an observation to the design, and the observation is slower, then not everything's going to be removed. Now, maybe some of them are going to be removed, and we'll come back to that, figure out how many exactly. But that's the principle there. Whereas if some other particle we observed came through like that, this is Vs2, so it was like Vs2 was greater than V naught, then all of them are removed, because we know that the particle that's least likely to be removed up there was removed. That means all of them will be removed. Okay, so pretty simple there. I just wanted to kind of start you in line in thinking in terms of comparing the Vs that we observed to the V naught. Okay. I don't think I had anything more to say about that exactly. Might come back if I want to draw something else on that slide. Okay, I did mention already that we can use either type of reactor. We can use a rectangular sedimentation basin or a circular one. And what's going to happen for the circular is we have motion, the water heading to the side like that. And the thing I want to highlight here is the area of the basin. And actually, I think that's what I was planning to talk about here. So the area of the basin is going to be important. So when I say area of the basin, what I'm talking about is if we look top down, that is this entire area, if this is an aerial view, or this entire area for this guy. However, if we draw this in this manner, like a cross-section like we have been doing, then the area of the basin, of course, is going to be, if this is the height instead of being like the width there, and this is the width here, and over here would be the length, then the area of the basin, what I'm talking about, is this. And likewise, if we were to draw the cylinder like a cylindrical system and say that that's like that, obviously not drawn perfectly, but then we're talking about the area on the bottom here. Get rid of that. I mean, still the water is going to move from the center of it to the side. That stays the same here in this picture, but that's what I'm referring to when I'm talking about the area of the basin for these two graphics. So I'm going to keep this one a little bit simple here. I'm going to go back a slide and talk about this. Okay, so in this case, what I want to show you is how we can relate the design criteria, the V naught, to the area of the basin, because it turns out that the height of the basin is not actually super important. So we've got height there, we've got length here, and width here. So this is our sedimentation chamber. And we want to know essentially how we can design the system in the most simple terms to satisfy our V naught. So a moment ago we said, for our design criteria, this is going to be equal to the height of the thing divided by the hydraulic resonance time. Well, if we think about it, we can say that's equal to height divided by V over Q, right? Because hydraulic resonance time is V over Q. And if we take that volume term we recognize that's going to be length times width times height, right? Or in the case of a circular one, we take pi r squared. Okay, so this height then, we can rewrite this and say that's the height divided by height times width times length divided by q. And we notice that our heights are going to cancel and that q term can come to the top. So we say, okay, well, this is equal to the flow rate divided by the width times the length. And the width times the length is that area of the basin here. So this is our AB. Then we can say the V naught equals, so V naught equals Q over the area of the basin. So in an interesting turn of events, we don't care about the height, we just care about the width and the length. Of course, the height still is in that information in terms of that flow rate because it's some amount of flow rate going through the system. And if you imagine I were to take some water in a bottle and pour it through a narrow trough, it's not going to occupy a whole lot of area width-wise. I mean, it could go for a very long way, but it would probably be deeper if I channelized it that way. Whereas if I let it go straight out on like an open table, it would spread out quite a lot. And so the height doesn't matter so much because it's going to normalize based on the area it's got to flow over, right? So the height's going to change based on that area and that flow rate that I'm passing through it. So if you think about a river going from a very wide channel into a very narrow channel, if it's going the same speed, then that channel has gotten a lot deeper, or it's just going a lot faster. You know, those dynamics are all put into there and all work together, and we get a very handy relationship here where our design criteria is just related to the flow rate and the area that we're flowing over. So that will be useful. Remember that piece. And like I said, that's going to be the same for both of these cases. V naught equals Q over AB. And so AB might be length times width, or it might be pi r squared. Or of course you could take a diameter instead of a radius. Okay, does that make sense? All right, so that one, I don't know if I put that on the equation sheet. It's simple enough that I feel like you guys can remember that, derive that if you need it. This is really first principles physics stuff here. You know, the particle needs to settle a length h. You've got time, which is your amount of time the water is going to be in that reactor. So certainly take the time to make sure you're very familiar with that, if that was any trouble. Wanted to mention kind of a neat tangent here. You can get a high rate settler by increasing that area of the basin. So if you were to just simply add shelves to your system, you have this. If I can draw, that would be good. If you have this system, and you have this clarifier, and normally you're limited to the area of this basin down here, and you decide, well, I want to expand the area, but I don't have any more space and any more land. Well, one thing you can do is just add shelves. And so then you've quadrupled your surface area here. You probably have increased the maintenance requirements in terms of, okay, we've got more moving parts, maybe some mechanical scrapers, some potential to kick up sediment and get it into your outflow when you didn't want it. So there's some mechanical and design challenges involved with doing this, but it can be a pretty reasonable way to increase your surface area and have a high rate settler by adding these shelves, because essentially each one of them is an extra area of the basin if you were to fill the whole thing with it. Because for particle sedimentation, really what you need is it just to contact a surface, and then you've got all sorts of drag acting on that particle from that surface, and it's just going to accumulate a layer there. And so assuming that you can shut down your process and scrape it away carefully or use a vacuum or whatever you're going to do, assuming you have a reasonable system in place, you can just add more shelves, and then you have high rate settlers. In this case, the particle removal, you're still with the case where if your VS is, or excuse me, if your V naught is less than or equal to VS, you've got 100% removal. And one thing you'll notice is that V naught has changed to be here. If I could draw that properly. So you can settle with a lot higher of a flow rate. So either you can settle slower particles, or you could just operate with a faster speed. So that's why we call it high rate settlers, because you can operate at a higher flow rate. In this case, if you don't meet that, then chances are pretty good that most of your particles will escape. I think this is not truly 0%. I don't think that's exactly right. I think I accidentally borrowed that from another slide, but you're not guaranteed very many particles. Yeah.
Couldn't you just make the tank just like not as tall or shallower and like achieve the same thing?
So the question is, couldn't you achieve the same thing by making the tank shallower? Well, the thing is, you can't flow as much water through if it's shallower, right? So then your flow rate has to increase. So it's not exactly like you could have the same change in the distance the particle has to fall. But again, think about if you had to treat 100 million gallons per day and you had a very tall, big chamber, that accommodates a lot of flow rate. And if then you're trying to make that a high rate, and instead of adding shelves, you just operate it with a lower ceiling there, so less water in it, you have to increase your flow rate if you're going to treat the same amount of water, right? So a lot of times what we're thinking about is treating some amount of water, and how do we design something so that we can achieve that. So yes and no there is kind of the answer. And I would say technically no for the flow rate reason, but yes, you could do that if you can afford to reduce your flow rate. Yeah. And again, that all relates to that settling velocity being related to Q and being related to the area of the basin. Okay, it's a good question. Okay, there's one other kind of funny design I'd like to draw your attention to, and this part is entirely true here. So this is called an upflow sedimentation chamber or design, and essentially what we have here is this is another cross section, but instead of flowing across like this, we are actually flowing upwards. So instead of that, our flow rate is going up. Water is being collected off the top. So it's like you take a cup, you put a pipe in the bottom, and you're adding water to it, and it just overflows off the top of the cup. Okay, so it's kind of a strange design here, and they're typically trapezoidal like this, so that as the water is heading upwards, there's actually more space for it to occupy, and in some sense, you're increasing the area of the basin in that manner. And so as the velocity, we'll say the velocity of the water going upward, it will slow down as it's going. And so at the very top, it's kind of a smaller term here. That VW, velocity of the water, has slowed down a fair bit. Okay, so this is a strange system because here, instead of settling in some amount of time, you have to settle faster than the water is flowing upwards. So in a way, it's pretty counterintuitive. That's not going to work too well for light particles that are, going to be pushed by the water pretty quickly and not essentially not settling very fast. So your V critical is going to be essentially equal to that velocity of the water going over it. And so what we have here is that, well, what I'll say is the velocity of the water has to be equal, is essentially V naught in a way, but it's negative V naught. And so if the particle settling matches that, it'll just barely not make it over. And so if it doesn't make it over, chances are it'll collide with some other particles. In reality, it would stick to them probably, and then they'd form larger particles and start sinking. But whatever happens, if it's at all lower, if the speed at which the water is going over is at all lower than the speed at which the particles will settle, then the particles will all be removed. So none of the particles will push past the barrier and flow over the system because they are now sinking faster than the water is moving over the edge. However, even if down here the particles are not quite making it, maybe it's a kind of a small velocity term, so long as the water slows down enough as it's heading upwards, then it can make it and it'll work and it'll be just fine. So it's kind of an interesting case. Is definitely all or nothing. That high rate settling is almost all or nothing, maybe not quite. This one certainly is. It's not used particularly often, but it is a reactor design I thought it was interesting and worth telling you about. Not really going to test you on these, I don't expect. Okay, so back to kind of the conventional case of this rectangular system, whether that's a circular basin or a rectangular basin. We can look at the rectangular cross section, water flowing through over. One question you might ask yourself is, okay, well, what if we missed the mark a little bit on a conventional system? What percent of particles are we going to remove from that? And so that's pretty handy to know. Let's say we have these velocity lines I drew here, giving me a line drawing envy because I can't draw that straight. So we see here that the highest particle does not make it. But some other particle, we'll say HP here, I guess, that one did make it, right? So how can we tell something about what portion of particles will be settled? Well, it turns out that given that we're dealing with velocities, we assume the particles reach this terminal velocity pretty quickly. It's actually some simple geometry is going to tell us exactly what fraction of the particles are going to settle out. So we can take a look at this portion of the space here that's missing. This amount of particles were not removed. That's the same as saying this amount here. So that's equivalent there. And essentially, with a bit of geometry, we can say, well, if our V naught is this guy, that line, well, we can compare the Vs to the V naught and see essentially what portion of this entire height was removed. And so if we look at it on this side, this entire water column has particles, and we're assuming they're evenly distributed throughout that water column. Then only this part escapes and this part is removed. Okay, and that's going to relate directly to our Vs. So we can say the percentage of particles, if we look at that, we'll say that Vs divided by V naught. So if, again, this is Vs here. If we take that ratio there, what what we're doing essentially is if Vs is equal to, what I'll do is I'll say Vs here, of course, Vs here as well. I will define this as height of the particle here, the particle that was settled for the Vs case. So if we say that this is equal to, so Vs being the height of the particle that was settled, divided by our theta, and then V naught is the height of the system. If a particle is at the height of the system, that's our critical design velocity divided by theta. Then what we see here is essentially what we're saying is the height of the particle divided by the height of the total. And so to get the fraction that is removed, that's how we get that relationship. And that's why it makes sense. We can just simply compare the velocities because there's nothing else that's changing. It's just really the height that it traveled. Okay, so looking at it that way, we can find that fraction that was removed and multiply that by 100% to go from the fraction to a percentage. Okay. Does that make sense? All right, so sedimentation, overall, fairly simple. Certainly a few calculations to be done. We'll use that settling velocity term, and we will kind of take a look at how to use that and how to manipulate that if we have different conditions. Maybe we have a few different particle sizes and we want to know what percent of each of them are going to be removed in a system. We can certainly do that. Maybe a temperature change shocks the system. How does that affect our particle removal? We can solve for that. Okay, here's a practice problem. Since I'm trying to move forward into the coagulation, I'm going to just point you to this. This is in the book, example 6.1. I'll read through it and let you try it on your own outside of class time. Essentially what it's looking for is, so we've got a circular clarifier, and the first question is, what is the hydraulic detention time? So we're looking for theta and whether or not it will remove all the particles given the parameters that it's given. So I'll read it through it real quick. Got a drinking water treatment plant, uses a circular sedimentation basin to treat 3 million gallons per day of river water. Gives us some information about MGDs. After a storm occurs upstream, the river often carries 0.01 millimeter silt particles with an average density of 2.2 grams per centimeter squared or cubed. The silt must be removed before the water can be used. The plant's clarifier is 3.5 meters deep, 21 meters diameter, so certainly not drawn to scale here. And the water is 15 degrees Celsius. Okay, so it's asking for theta, and then it's asking for essentially all particles removed. Those are the two questions. And one thing I'll note here is make sure you're tracking your units. If you take a look back at our velocity equation, it was g times rho minus rho p times diameter of the particle squared times divided by 18 mu. Pay attention to those units there because you're going to need meters, not millimeters. You're going to need kilograms per cubic meter so that your meters match up with your densities. The acceleration due to gravity, we typically write in meters and seconds. And so make sure all of your units are consistent so that you can end up with some meters per second value. Okay, so if you do all those pieces, it becomes pretty simple. Just pay attention to those pieces and make sure you work through it to get those points in line. Okay, so with that, I know that was a little rushed, more so than I wanted, but that's essentially sedimentation. At the end of the day, it won't be too complicated. Once you get some practice, you'll get a good feel for it. The next thing in line is coagulant dosing, and this comes back to what we think of as one of our standard reactor types. This would be a CSTR. We don't really do a whole lot of reactor dynamics because it's just a small box that you pump in the chemicals to inject them as you're pumping the water through, and it just rapidly mixes them and goes on. That's the point. It's just a rapid mix step. So we could solve some stuff here, but we're not giving it enough time for any real reaction. It's just mixing the solution, and then reactions will start occurring in the flocculation chamber. But I want to go over some of the factors that regulate or that affect coagulation, what it is, why it works, some of that. So I'm going to talk about that for a few minutes. We'll just do a quick attendance thing after that. And I think next time we'll get into flocculation a little bit more. Okay, so the first thing you might want to ask yourself is, okay, well, what are we removing? And as you start practicing with the sedimentation, you'll notice that for basic sedimentation, it's kind of hard to remove anything that's really anything significantly lower than the 10, 20, 50 micrometer range particles. Like that stuff is pretty much the limit that a sedimentation basin of any reasonable size can handle. I mean, it depends on the density of the particle, right? But assuming that we have typical particles in water. So if we're looking and considering, okay, what's in sort of this range, maybe we can remove stuff that's generally visible to the human eye if you look closely. It's a nice little plot here of just stuff you can see, right? Got human hair, pollens. So sedimentation might be able to remove some pollen. If you had soil particles on here, you might have silt particles. Clay particles start getting into the realm of probably not removing directly. Certainly sand and anything larger could be sedimented pretty easily if it gets past a grit chamber. Perhaps some algae, but really not much in the way of pathogens. Maybe some large cysts, probably not for the most part unless we add the coagulation. So if we're interested in starting to catch some of the bacteria, some of the algae, some of these cysts, and clay particles, and whatever might be hanging onto the clay particles, maybe some bacteria stuck to the clays, and other just whatever particles exist, that doesn't have to be a clay, maybe it's what we would normally think of as dust, just sort of fine debris. If we wanted to start removing that type of stuff because it would scatter light in a UV process, or it would maybe shield bacteria from chlorination, definitely want to get rid of it as much as we can. We have to do something to start catching these particles, making them stick together and grow in size so that they could be removed more easily. I'll just remind you real quick, our equation here, G is not really going to change. It'd be hard to change the density of water reasonably. Maybe we could change the density of a particle, but that's not very convenient. And so if we look at what else we might be able to change, that diameter of the particle, first of all, it's related to a square. So whatever change we make in the diameter is going to be a lot more effective than a change in the density of the particle. So if we can cause particles to stick together, even if the density doesn't change at all, nothing else changes, that diameter change is going to make a big impact in the settling velocity. So with adding a coagulant, a large part of what we're aiming at is changing the diameter of particles. The way we do that is to manipulate particle stability. So why do particles float around and not stick together in the first place is a reasonable question, because some particles, you could see it if you mix some particles into water. Sometimes they'll stick together and form larger particles. Sometimes they'll just stick to the edges of the bottle or the cup or whatever, or sometimes they'll just sit there and float. And you might ask yourself, well, why is that? And why do it turns out most environmental particles in water, if they're floating around, they're going to be stabilized in relation to one another or to other surfaces. So what we mean by stabilized is really that they're stable and not sticking when they interact with another surface. So that's what we mean when we say stable. Generally, the way this occurs is they have some surface charge. A lot of particles will have a net negative surface charge, even if it's not like they're, maybe they have positive charges within the molecules that they consist of or whatever. But as a whole, they'll typically have a negative surface charge. That has a little bit to do with type of chemistry. A lot of times there'll be, like carboxyl groups and stuff. Maybe you have a carbon and something like this, and then you have an OH group there that can lose the H, and then you have CO and a minus there, something to this effect. That would have some other stuff there. That type of acid-base chemistry often gives you a net negative charge. As a variety of functional groups that can do that. Just a quick example of something that can do that, give you some negative charge. And so on the whole, if a particle is stable in water, a lot of times they have this negative charge. And that negative charge essentially keeps some repulsion between particles because the negative repels the negative. And in fact, it's a little bit more complicated than this because if the particle itself has that negative charge, it's going to attract positive ions in solution. And then those positive ions in solution that are kind of sitting up next to it, they're going to attract another layer, but it becomes more and more loose and disorganized as you go. And so essentially we get a double layer of ions that kind of hang around, and maybe some extra positive ions come around or whatever. But essentially we get this effect where we have this double layer. We have a charged surface that attracts a layer of ions, which attracts a second layer of ions, and we get this electrical double layer is what we call it, so EDL. And essentially that net double layer is giving some cushion between particles that exerts some force on each other, and it extends some distance away from the particle. So we have some distance here, and maybe this is, 15 nanometers or something. It's some amount of space that actually has a significant distance based on how many ions are in solution, how charged the surface is, and some factors like that. And really, it's a force balance here between this electrostatic repulsion and forces that we call van der Waals, which are sticky forces, attractive forces. It's the type of forces that allow a gecko to climb on a perfectly flat surface. These van der Waals forces, there's a variety of them, but they're generally attractive, but they're short range. And so if we can get if we can overcome the repulsive force of that electrical double layer so that we can make use of the attractive forces of the van der Waals, then we can cause the particles to stick together. So when we talk about particle stability, what we're talking about is which force is dominating. If they are stable, then this repulsive force is dominating. If we have destabilized them, we've somehow gotten rid of or reduced the length of this repulsion. And so then when the particles randomly meet from diffusion or whatever, then they'll stick together, and that's called destabilized, so that they stick together, and then they're larger particles suddenly more likely to settle out. Okay, so here's another diagram of what I'm talking about there. This solid surface you would think has kind of a negative charge throughout it, and then you'll see this positive layer and then kind of a negative layer coming on top of it. That's the dynamic that we're talking about. Now, the extent to which this happens depends on how many ions are in solution. If we have really, really pure water, then maybe you just have a few sodiums or chlorides, maybe not even that. Maybe you just have H plus and OH minus. And if you remember from chemistry, those are going to be something like 10 to the minus 7 moles per liter. So very sparse. So if that's what you're relying on, this double layer is still going to have an impact. You're still going to be attracting charges, and the charges are going to want to align with opposite charges, but it's going to stretch that double layer way out into solution. So depending on how pure or how salty your water is, that's going to dictate the length of your system here. So conversely, we can add salt or add ions to shrink that double layer. And that is exactly what we do with coagulation. So coagulation, that's one way in which we do it. I'll explain this slide, and then we'll do the quick attendance, and then that'll be it. Okay, so we can take a look at the amount of particles in water, maybe a turbidity measurement. So turbidity is light scattering by particles. So it's a measure of how many particles there are. And that's what this graph here is showing. So the way we measure turbidity, turbidity really is an estimate of amount of particles. And we do that by measuring how much light they scatter. We'll talk more about that later. So essentially we can take that measurement and say, okay, well, if we have 100% turbidity or remaining turbidity, it had some amount of turbidity and it's still 100%, that means no particles have been removed. They're all still stable, they're still floating around there. Then in this graph, if we take a look and say, oh, suddenly we've been adding something and suddenly the particle turbidity or the turbidity value drops off a cliff here, well, that shows us that we've suddenly destabilized the particles. So one thing to note here is we're adding aluminum and it destabilizes particles quite well with just 10 milligrams per liter of the aluminum. We can keep going with calcium. So calcium, if we take it, nothing's happening. Suddenly they get destabilized around 100 milligrams per liter. Likewise, we could destabilize particles with sodium, but it's all the way up at 10,000 milligrams per liter. The reason that's happening is if each of these little ions is a sodium, you need one sodium per spot here, whereas if you could capture 3 spots with just one atom, 3 charges, so one aluminum atom would fill quite a lot of space. So it condenses it. It condenses the amount of ions that are needed, and it does so more than just a linear relationship because each ion is occupying so much smaller amount of space and satisfying so much more charge, it has a much stronger effect. So calcium would do 2, and the sodium 1, and aluminum here would do 3. So the charge here is actually a big deal, and that relates to our ionic strength. You may remember ionic strength equation is 1/2 times, we could do it this way, the sum of the charge of some particle squared. So charge is a particle, so Zi Ci times the concentration. So we'll work through some of those later, but should be familiar with that from some chemistry class, I would guess. It's pretty simple to calculate the ionic strength. Okay, we'll make sure you have some practice with that. But so all that to say, the ionic strength makes a big difference. These 2 graphs on the left kind of show a different view of that. essentially looking at the distance at which you can detect the double layer. So the double layer is observed in millivolts. That's so the charge that we're detecting there. How far into solution away from a surface can we detect it, based on adding either different amounts of sodium chloride or adding particle ions with different charge, so sodium, calcium, or aluminum. And so you can kind of see how that affects the distance here in nanometers. You know, if we were to select, let's say 40 millivolts, if we're adding the same dose of sodium chloride, that goes out to 20 something nanometers. That's plenty of space to keep a particle stable still. Whereas if we got aluminum, that's less than 10 nanometers. And really, if you want to destabilize particles, you do need to get around 6 to 10 nanometers, something like that, or smaller. So some cool visualizations here about how that works. And okay, with that, let me just load up Kahoot. We'll do a quick activity, and that'll be it for the day. All right. So just put in your 89 number and answer anything. It's fine. I will post your first homework today, hopefully in a couple hours. I did post Tuesday's slides to Moodle. I will post the lecture soon. But remember, you can always access these lectures on Twitch. They stay there for a couple weeks or 10 days or something like that. So certainly I will download and upload the video to make sure you have them all semester. But if you ever are in a hurry and want to watch them sooner than that, just head over to Twitch and you can catch them there. Okay. See, 2 viewers online, 9 in class. So. All right. So thank you guys. Well, have a good weekend. See you next week. Stay dry if you can. For the viewers online, maybe there's too much lag here. I'll type a message to you. All right. See you guys.
The for the honors option, I sent in the